Now we can take any section cut as shown by this light gray area and look at the stresses inside of it. And the first thing we notice is that the shear stress will distribute evenly throughout the entire area, giving us shear stresses in the vertical direction. And we notice that a small portion of the bending moment will induce a force distributed evenly throughout the small gray area, giving us a normal stress that increases the further you get away from the neutral axis, where there's zero normal stress, as shown by these longitudinal blue arrows. And notice that the bottom of the section is in tension and the top of the section is in compression. And adding up all these small moments sweeping across the entire area of the section will give us the total moment at that section. And putting this all together, we can conclude that the normal stress at any vertical point in this section is proportional to the entire moment and the distance from the neutral axis divided by the area moment of inertia, or the member's resistance to bending. And what we can do from that is we can draw a stress element at any position, and we can see that the normal stress will stretch the element horizontally, and the shear stress will deform the element into a diamond or parallelogram shape. So I took the liberty of compiling all of the input parameters and equations that we derived into this handy spreadsheet so we can easily achieve and view the desired results. So I have any inputs in light blue, such as the geometry, forces, properties of the material in section, and any boundary conditions that we know, along with any guesses, such as the internal moments at the boundaries. Then I have a column that everything is dependent off of as x, or the distance from the left boundary to that section cut of interest, and columns for the numeric values, which takes the previous value and adds that small change of that value to get the next value of interest, effectively summing all those small areas. And then columns for analytic solutions, which takes the exact area achieved by integration. And that gives us solution curves for the internal shear, the internal moment, and the slope, and the displacement across the entire length of that member. And I have denoted the light color as the approximate solution and the darker color as the exact solution. And I would include a link for all this in the description. So I encourage you to play around with different geometry, forces, and material cross sections and see what results arise. So to kind of summarize here, we first took the loads applied at the given beam geometry and found the force reactions at the boundaries for equilibrium, transferring shear force from section to section along the entire length of the member. Then by guessing the reaction moments at the boundaries, we determine the moments transferred to each individual section which bends the beam, changing the slope of each small section, effectively displacing the beam vertically. Then we were able to compare the result of the slope and displacement at the right boundary and re-guess the moments until we got effectively close enough to the solution. Then we were able to probe different points in the cross-section of the member and found the shear and normal stresses, which you can compare to the material strength to tell if the material will crack or fail. And a few concluding thoughts here. So just because something seems undefinable at the time doesn't mean there's not a solution. It first helps to question the nature of a tangible real-life scenario, which in turn breathes the necessity to dive into the mathematics. And good luck finding an explicit solution for the boundary moments, but fortunately they can be determined iteratively and implicitly. So don't give up, just need to dig a little bit deeper into the problem and continue to define what you know. And it's so easy to blindly apply and get lost in the equations without gaining a real understanding of what's actually going on or what it's describing. So the strategic simplification of the system is your best friend. And even this relatively uniform one-dimensional system almost reaches the limit of what we can define. I encourage you to maybe try a two-dimensional case. And I hope you found this informative and your intuition sharpened. And please post any questions in the comments, and I'd be happy to see if I have an answer for them. And like and subscribe if you found this construct fascinating and like to see something more in the future.